Hello. So, in the last class, we ended by talking about the different attributes of turbulence. We talked about the disorganized, chaotic nature, the non repeatability, and that had to do with the sensitivity to initial conditions, the large range of length scales and time scales. Of course, we've talked about that right from the first class. The enhanced diffusive mixing, right? That is related to the convective term, the Navier-Stokes equations. The dissipation at the small scales due to viscosity. The three-dimensionality. Remember, turbulence is 3D, not 1D or 2D. No matter what kind of chaotic solutions you get from 1D or 2D Navier-Stokes equations, from the solutions of 1D or 2D Navier-Stokes equations, that might not necessarily be turbulence. The rotationality. Okay, we'll talk more about that in detail in the coming classes. And then finally, intermittency, like I was describing earlier. So now that we have described the attributes of turbulence, why don't we try to look at a brief history of how scientists and mathematicians have tried to understand turbulence. So from the 1500, we know that Da Vinci had described turbulence, right? As it described it as a distinguished physical phenomenon. And Da Vinci drew a sketch about it and described it as turbulenza. But since then, for about 200 years or so, 200, 300 years or so, there have not been much developments in turbulence. Around 1877 is when the business developed his hypothesis that turbulence stresses are linearly proportional to the mean strain rates. So interestingly, where does this come from? Okay, so if I write this equation out, I have tau is proportional to the mean strain rate. So let me just call it Sij bar. Okay, Sij bar representing the fact that it is a mean strain rate. Sij is the strain rate, and the turbulence stress, let me call it tau. In fact, I will call it tau with a subscript T, representing turbulence stress. So what Bissonnette hypothesized is that the turbulence stress is proportional to the mean strain rate. In the same way as stress, according to Newton's law, is proportional to strain rate. So that is gamma dot is what I'm calling strain rate. Now keep in mind, this proportionality constant is mu gamma dot. Okay, so tau is equal to mu gamma dot. This is what we know as Newton's law of viscosity. The shear stress is proportional to strain rate, and the proportionality constant is the viscosity. In the same way, Bissonnette hypothesized that analogous to the shear stress strain rate behavior, that particular relationship, how about there could be something like tau t is equal to mu t Sij mean. Okay, mu t Sij mean, where mu t is the eddy viscosity or the turbulent viscosity. So you can see the analogy here. In the same way as stress is proportional to strain in any kind of flow, right? Total stress is proportional to strain. Laminar flow, turbulent flow. Specifically in turbulent flow, how about we have a relationship where you have turbulent stress is proportional to the mean strain rate. Remember, you have to include mean here in turbulent flows because you have a fluctuating flow. You have a flow that is dependent on time. Okay, interesting, isn't it? Now, Bissonnette himself offered a warning to using this hypothesis because experimental observations and others might showed that this might not actually be true. In spite of that, we still use this hypothesis for the development of a lot of turbulence models. Almost 300 years later, we are still using the same hypothesis. tau t is proportional to the mean strain rate. Mean because it is a turbulent flow and the flow is dependent on time. So you have to take an average over time. That is why it is mean strain rate. The proportionality constant in this case is a turbulent viscosity, not your molecular viscosity like you have here. Okay, it is a turbulent viscosity. It is not a molecular property. Again, we'll discuss more of that in the coming classes. So that was in 1877. Moving on, in 1894, one of the most influential results came out through Osborne-Reynolds experiments. We have discussed those experiments as well in the previous class, where he observed the transition from laminar to turbulent flow as he increased the flow rate or as he increased the velocity. And he developed one single parameter, what we call a bifurcation parameter. Now we call that Reynolds number, which determined the characteristic of the flow. So this led to the identification that Reynolds number is the only physical parameter that is involved in the transition to turbulence. That parameter alone can determine whether your flow is laminar or turbulent. You don't have to look at velocity, density, viscosity, or length scale separately. You can look at all of this bulked up together as a single non-dimensional parameter called the Reynolds number, which we now call the Reynolds number. So the view and analysis in this paper has basically led to turbulence being seen as composed of a mean part and a fluctuating part. And this has a lot of implications coming later. We'll talk about it too. So in the sense, we call a Reynolds decomposition as the following. Any flow variable, and for now I'm just going to take velocity u, is equal to u bar plus u prime. This is the Reynolds decomposition. So I am decomposing it into a mean and a fluctuating part. Okay, I am decomposing it into a mean and a fluctuating part. U on the left hand side is the instantaneous velocity. That is decomposed into a mean velocity plus a fluctuating velocity. So this led to sort of a prevailing view at that time and many more years later that there's probably not a lot of information that can be gained from analyzing the fluctuating part. That led to sort of the statistical view of turbulence, as in, why don't we just look at the mean of the flow? The fluctuating part is random anyway, although we now know that is not the case. It is not exactly random, it is seemingly random. But there was a prevailing view in the early 19th century, in the early 20th century, where the mean was sufficient to be looked and the fluctuating part was random, so there's not a lot of information that can be obtained from a random component. Why don't we just look at the statistics, the mean? So that was around in 1894, early 1900s. Now, towards the beginning of 20th century, Prandtl came up with a seminal theory called the mixing link theory. So this was in 1925. Following Reynolds' first major result, Prandtl, in the form of a prediction of eddy viscosity, the same eddy viscosity that I had described earlier for the Bismuth hypothesis, he established the mixing length theory. And this again was analogous to the kinetic theory of gases. So this is coming from the kinetic theory of gases. According to the kinetic theory of gases, you have random motion of molecules. You have random motion of molecules. Molecules are moving randomly, they collide and they impart energy to the neighboring molecules. So any property of a fluid is an average of the property of these molecules. So this is how every property is described for a fluid. It is due to the random motion of molecules within. Now, agreed, in fluid mechanics, we are invoking the continuum hypothesis. So we are not looking at molecules, we are looking at fluid particles. However, he used this concept to describe the mixing length theory. So if I go to the next slide, I have a figure illustrating what the mixing length theory is. So the mixing length he described as the distance a fluid parcel will keep its original characteristics before dispersing it to the surrounding medium. So that is what is described here. This is what I'm calling the mixing length. So here, that is the mixing length where the distance a fluid parcel, a fluid particle, has to travel before it disperses its characteristics to the surrounding medium. That could be momentum, right? That could be energy. In the same way as molecules that travel randomly within a domain, they impart energy to the neighboring molecules through collision. The mixing length is defined like that. So that is the mixing length theory. And this is being used for the development of turbulence models as well. So that was Prandtl's mixing length theory. Moving on, around 1935, Taylor explicitly presented the assumption that turbulence is a random phenomenon. So this was a time when the prevailing view was that turbulence is a random phenomenon. So he introduced several statistical tools for an analysis of homogeneous and isotropic turbulence. So homogeneous turbulence means the statistics are invariant with space, and isotropic means they are invariant of direction. So we will describe all of these in detail later, but that's what Taylor came up with, and he developed an experiment in the context of a wind tunnel experiment to convert temporal data into spatial data. So temporal data would be the decay of turbulence. As the flow travels from one end to the other, there's a decay in turbulence, and he developed a method to convert that temporal data, as in how the statistics varied with time. He developed a way to convert that into spatial data. Then came the theories of Kolmogorov in the 1940s, where he published 3 seminal papers related to providing theories for the way the energy cascaded from large scales to small scales. So one seminal theory was the K41 theory, which several years later, scientists discovered the importance of this theory and started using that for different correlations. Even to date, these theories are used for validating simulations, validating experiments, and trying to understand different correlations. The K41 theory and K62 theory, which is not as popular as the K41 theory, came to be known. So when Kolmogorov wrote those papers, the value of actually those theories were understood much later, several years later. Then in the 1940s, there were several works of Batchelor, Burgers, Corson, Heisenberg, von Karman, Obukhov, Townsend, and Yaglom. 50s, there were several books by Batchelor and Townsend and Hines, seminal books which are still used to date. And then in the 1960s came a seismic shift in the way we started to understand turbulence. And that was because the advent of the first generation of computers. So Lawrence at MIT started using machinic computations for a deterministic solution of the Navier-Stokes equations to solve the equations. He found those to be random at that time. He could not distinguish it from random, but he showed that they were sensitive to initial conditions. And this was later shown to be associated to the strange attractor theory in mathematics. But we'll describe that in more detail. But this was sort of a momentous shift in the understanding of turbulence, where the sensitivity to initial conditions was first shown. We'll in fact show some of the results of Lorentz in a couple of modules later. And then in 1950s again, a new direction started to be taken up to understand turbulence. the closure problem of turbulence started to gain more prominence. The closure problem meaning the existence of more unknowns than equations. Obviously, as you know, if you have multiple equations, if you have more unknowns than the number of equations, the problem is unsolvable. And that is exactly what you get with turbulence. If you average out the equations, and we will go through that exercise where we take the average of the Navier-Stokes equations, you will end up getting terms where you have more unknowns than the number of equations. And this is one of the problems with looking at turbulence from a statistical point of view, where if you focus all your attention on just the mean and not the fluctuating part, you will end up in a situation where you will have the actual closure problem. Okay, again, these things are going to be described later as well. In 1971, there was the seminal paper of Roll and Takens. They had the modern view of turbulence, the modern definition of turbulence sort of came from their paper, where they showed, they presented the fact that Navier-Stokes equations could produce deterministic solutions, exhibiting sensitivity to initial conditions. SIC is sensitivity to initial conditions, and associated that to a concept called a strange attractor theory. Okay, so what they showed was that there would be a sequence of transitions that the flow would undergo as the Reynolds number increases, from steady to periodic to quasi-periodic to turbulent. And in fact, you can see that this has been shown in several calculations. The typical benchmark problem of flow over a cylinder, okay, you will see that as at very low Reynolds numbers, for instance, the flow will be steady and the flow patterns will look like this. Streamlines that are perfectly smooth, and the flow looks very smooth, and in fact it will be steady. Okay, this is for very low Reynolds number. So for example, Reynolds number of the order of 10. As you keep increasing the Reynolds number, say to 50 to 100, you will start to see that there would be some periodic flows. For example, if you at 150, you will start to see vortex rings being formed, which dissipate and eventually form. So then you will have a periodic flow. Okay, so for example, this is at Reynolds number of 150. You keep increasing the Reynolds number, you will get quasi-periodic flow. So it looks periodic, but it is not periodic. And then you will have a fully turbulent flow at Reynolds numbers of 5,000 to 10,000 or so. So that's a perfect example of how you will have a sequence of transitions as the Reynolds number increases. Moving on, from the 1970s and 80s, experiments started to be developed more, and the visualization developed a lot more to understanding turbulence. The experiment by Figengau, Manivelle, Golub and Benson, Blackwelder, Antonia, Reynolds and Hussein, Bradshaw and co-workers. 70s to 80s, there were huge advances in computational techniques. DNS, direct numerical simulation, started to be more developed. Orszag and Patterson's work on DNS are quite seminal. Large eddy simulations started to be developed in the early 80s and late 80s as well. RANS started to become more popular due to its computational efficiency. Launder and Spalding were very important in developing RANS methods. And then in the 1990s, computational techniques started to be more developed, computers started to be more powerful, and there was a tremendous amount of research put on LES, large eddy simulations. You can see this in reviews of Lesueur and Matars, Menevue and Katz, and as well as Sagut as well. So in all this history, you will notice that there were three kinds of movements in the way physicists and mathematicians studied turbulence. And we classify that into 3 eras of turbulence studies. This is according to Chapman and Toberg's 1981 paper. The statistical movement, the structural movement, and the deterministic movement. And they in their paper actually have classified the different physicists who come under those categories. The statistical movement would be something like you are looking at the statistics of turbulence. So that is the prevailing view that came out of, in fact, Reynolds experiments where you could, and the Reynolds decomposition where you could decompose a flow variable into mean and a fluctuating part. The fluctuating part being random, the prevailing view at that time. So the mean, let's focus on the mean. So the statistical movement would be that, mostly assuming that turbulence is a random phenomenon. The structural movement started much later, and there the idea was to look at the structures that were developed in turbulence, the vorticity magnitude, how the vortex structures developed, and try to understand turbulence from that perspective. And the deterministic movement comes from the solution of the Navier-Stokes equations, because the Navier-Stokes equations are what are deterministic. So obviously that could only come about once computers started to be more popular. So that is why you will see that the deterministic movement is the one that started and started the latest, right? In the 1900s, Poincare, Leray, they talked about the Navier-Stokes equations in terms of the solutions of those, but actual solutions could only come once once machine computations were developed. That was by Lorentz in the late 1960s. So what does this all mean, right? The statistical approach is motivated by the view that turbulence must surely be random. Okay? And in fact, repeated experimental contradictions of this interpretation, we see that the statistical movement has extended all the way to even today, where Reynolds average Navier-Stokes approach, the Reynolds average Navier-Stokes approach, which is even used today, and the LES approach, the large eddy simulation approach, assumes that the mean is what is more important. Why don't we focus on the mean? So here, that statistical approach is still used. So somewhere there is an assumption that the fluctuating part is random. Now, one of the more interesting contradictions of this era arises from the fact that many researchers were already accepting the Navier-Stokes equations as the correct formulation of turbulent flow, isn't it? So then how is it possible to describe a random phenomena using Navier-Stokes equations which are actually deterministic? Can a deterministic equation exhibit a random solution? So Chapman and Toberg in the 1980s in their paper, mentioned that solutions to Navier-Stokes equations are deterministic. So that means that leaves us two choices. Either accept the Navier-Stokes equations as the correct description of the turbulent flow and admit that turbulence is not random, or you have to seek a completely different description. Then you have to admit that Navier-Stokes equations are not the set of equations that represent turbulent flow. Maybe there are some other equations that represent turbulent flow, say a set of stochastic differential equations. However, we now know that the Navier-Stokes equations are complete in describing the turbulent flow. But this was the inherent view a few decades back. So if we insist, now the problem doesn't go away, right? If we insist that turbulence is a random phenomena, then averaging the Navier-Stokes equations as is done in Rand's approaches might make little sense. That's what Chapman and Toberg were arguing. So then we would be starting with the wrong equations and ending up with equations that are not stochastic. So that is what led to, say, the structural movement. So the structural movement is viewed by Chapman and Toberg as having begun possibly with some observations in the 1948, where even early experiments of Reynolds also showed, right, coherent structures in turbulence. So as the flow is turbulent, you see these fluctuations and you see the structures, coherent structures of flow. So even today, we can use some of this to see that there are structures that evolve, that break up into smaller and smaller structures, and you can try to understand turbulence using that. So that was the structural movement. And finally, in the result, what Chapman-Toback says is that they summarize the statistical movement as a structuralist theory with little power of conceptualization. So, and what they say is it has little power of prediction, at least in part, due to the lack of structure. So that's what they classify the statistical movement as. On the other hand, they describe the structural movement as a structure without theory. So, because when you're analyzing these structures, you're going to get massive amounts of data. So it is hard to construct a theory out of that. That is what Chapman and Toback argued. So after describing a considerable amount of research up to the 1984, they concluded that while the deterministic movement is encouraging, they had not yet provided a successful approach for simulating turbulent flows. And why is that? Right? The Navier-Stokes equations describe the turbulent flow completely. Then why is it that the Navier-Stokes equations are still not able to successfully simulate turbulent flows? That has to do with the fact that you have a wide range of scales in turbulent flow. If you were to describe a turbulent flow accurately, completely, then you would have to resolve every scale. That is where a direct numerical simulation comes into play. But even to date, direct numerical simulation is computationally very expensive for the most realistic turbulent flows. So in that sense, you would have to utilize some parts of the statistical movement and some parts of the structural movement as well. The deterministic approach cannot fully help us understand turbulence because of these limitations in computing power. Because of the wide range of length scales, resolving every length scale is difficult, is almost impossible. So direct numerical simulations has its limitations. And hence, a deterministic approach has its limitations in describing the turbulent flow completely. So hence, we would have to utilize some components of the statistical approach where you take a mean and a fluctuating, maybe like a large eddy simulation, which is decomposed into large scales and small scales. You use a subgrid scale model to model the small scales and you resolve the large scales exactly. That is a form of statistical approach. You use some parts of the structural approach, maybe look at coherent structures, see how they evolve, and that can help you gain understanding. So future approaches would utilize the deterministic approach. Yes, that's the way going forward, but you might have to incorporate some parts of the statistical and the structural components into your deterministic approach in order to gain a full understanding of turbulence. So what have we seen in this lecture? We have looked at mostly a history of how turbulence has been approached, starting from Da Vinci's description, jumped 300 years later to something like Reynolds' experiments, Prandtl's theory, several books, Taylor's hypothesis, the advent of computers, and several theories later. We are now at a point where we could use a deterministic approach. We now know that the Navier-Stokes equations describes turbulent flows exactly. So we could use a deterministic approach, but with parts of statistical and structural approaches in order to describe turbulence fully. Thank you.